Okay, so welcome back. I hope you had a good spring break. Little bit of relaxation, but not, you veer. I'm hoping you did not veer too far away from physics, right? Okay, so let's get started. So we will just do a quick review of the uh, multiple expansion that we are working on in the context of electrostatics. Then we will apply to magnetostatics, and then so you can kind of see the parallels. Plus, it allows us an opportunity to quickly uh, review magnetostatics as well. And then we will do multiple expansion in magnetostatics. So let me share the screen with you. Okay, there we have it. So this is what we're going to do. So let's do just a quick review of the dipole field that we did the other day. Uh, we calculated the field, um, but we kind of directly wrote down the expression for it in the 2D polar coordinates. So let's just do a recall. And when we recall, the electric field is negative gradient of the scalar potential, which for a dipole field. So this is what we are only looking at the dipole field for now. And the potential, anybody remembers what that looks like? So it still has the same constant in front as you would write the Coulomb law, but instead of rho over r, now it has the dipole moment dotted with the position coordinate of the point at which you're trying to find the scalar potential divided by r cubed. And r is much, much less than some characteristic length, which is, let's say, the size of the charge distribution that we have. So we had this diagram here, I believe. Yeah, so it's this kind of thing. Let's go back and put it here. So just to remind you, R is the blue circle. That's the characteristic length of your charge distribution, the largest one that you can find. And then after you do the gradient, you should do this exercise of taking the gradient of P dot R over R cube. P is a dipole moment, it's constant, so it does not have a gradient, but R itself, R over R cube, that's going to give you, obviously two terms. So this is something you can do. 3 R hat dotted with P minus the vector P itself divided by R cubed. And again, R is much, much less than the side. So you are at points really far away from the charge distribution. So let's take a look at now the polar coordinate calculation. Right, so let's draw a diagram of how the polar coordinates would look like. So that's two-dimensional 2D polar coordinates. Let's draw a vector R. At this point, we're trying to find the potential, and you have R and theta. And of course, you have the unit vectors is this way. Which way would you draw the unit vector for the theta direction? Any thoughts anybody wants to share? how should I draw the unit vector for the theta direction?
Perpendicular to R.
Perpendicular to R, which way should it go, up or should it go down?
Down.
Down. Right, just because of the way theta is measured, theta would be increasing in the direction of theta hat. That's how it should be. This is z hat. It's going, it's coming out of the plane of, yeah, this is measured with respect to the z direction. So this is not like the standard xy polar coordinates, slightly changed because we want to take p to be a vector in the z direction, right? And the angle is measured from the dipole, and that's why it looks weird like that. Now z hat, you can write it down as, so z hat is this one here. This vector here is z hat, right? You can write it down in terms of the r coordinate and the theta coordinate. So it is going to be r hat cosine theta. If you take r hat cosine theta, that's going to have a vertical component, and theta hat sine theta would also have a vertical component, but it's in the opposite direction. And so theta hat sine theta. That's how you can write down z hat. Z hat is going to be a combination of both r hat and theta hat. And how do we get that? You could just do a dot product of z with respect to r hat, and that will give you cosine theta, and dot product of z with respect to theta hat, that's going to give you negative sine theta, and that's how you know z hat is going to be a combination of those two. And so if you take now the dot product z with r, it is going to be just like I said, cosine theta. And so let's now take a look at this term, r multiplied by r hat dotted with p, right? We will need to write this down. This is going to be essentially r hat, then p cosine theta, right? Because it's p is in the z direction, you're trying to take a dot product with r hat, which is cosine theta, and the magnitude of p is p, right? So everybody with me with this? You understand? So that's the first term in the expression for the electric field, right? So this, let's highlight it. This is what we are trying to simplify right now. Okay, and that's just very simply is that. And p is just p, which is z hat, which we know already how to write down in terms of r and theta. And so now we are in a position to write down the total electric field vector, which is going to be p is going to be common, the amplitude of the dipole moment. So, and then you have 4 pi epsilon 0 r cubed, and the first term was 3 cosine theta r hat. That is the highlighted term. So I'm going to write it like this. And then the other term is basically negative of p, which is negative of r hat cosine theta plus theta hat sine theta. And then you can combine the r hat cosine theta terms, and then you get p over 4 pi epsilon 0 r cubed 2 cosine theta r hat plus sine theta theta hat. And this is the expression that I just kind of directly wrote down for you in the previous class. But now we know how to evaluate it by determining all of the related dot products. Everybody with me? Okay. Any questions anybody has? No questions? Okay. Um, I am having right now some issues with my Mathematica. I did not get to update it when they changed the license. And so I won't be able to plot this for you today, but I will get that thing resolved, and we will spend some time on use of Mathematica for plotting some of these vector fields uh, uh, on Thursday, right? So remind me if I forget. That's our plan for the next class on Thursday. We want to try to learn the use the graphical capabilities of Mathematica for uh, visualizing these complicated looking quantities. Okay. Any thoughts, questions? Okay, so now let's relate and connect uh, the uh, the dipole field that we have calculated with quantum mechanics. It turns out there is a uh, important and well-known connection between the two. Right? So let's take a look at it. And so I'm just going to first state the theorem, and then we will look at it mathematically just briefly. So well-known theorem of quantum mechanics states that remember the electric dipole. So what I wanted to say was the source of the electric field, which is the electric charges, they're not freely lying around in most cases. When you look at their atomic origin, so the origin lies into systems that are microscopic, and so those systems are governed by quantum mechanics, and so you cannot really separate these different areas of physics from each other. They affect each other, right? They are uh, uh, you cannot forget quantum mechanics completely even when you are doing a macroscopic theory of fields like electric field, for example. So electric dipole moment of any microscopic system is zero if its wave function has definite parity. Meaning when you change the coordinate r to minus r or x to minus x and so on, then because you are integrating over the whole volume of space, the positive terms would add up, the negative terms would cancel, and you get the dipole moment to be essentially zero. So rho of r. So if rho of r, let's say, has positive parity, r doesn't, right? And so you're going to get zero. If rho of r has negative parity, then also you're going to get essentially zero. So what we're talking about, not the sign of rho of r, that doesn't matter. It's how it is distributed in the space, right? So is it symmetrically distributed? So for example, if you have a charge distribution that is spherically symmetric, right? So let's draw a little circle here, and let's shade this if I could. So I want to shade it in such a way that I could show different regions. So I'm trying to emulate a spherically symmetric kind of charge distribution by showing you uh, rings of how this charge distribution is. Okay, I'm not doing such a good job there, but you get the idea. So these rings basically mean you have different contours of the charge density. So it doesn't have to be uniform, right? It can be radially varying, but as long as it has the spherical symmetry, then the dipole moment for this is going to be zero. Okay, that's what this tells us. So if you have isolated electrons, atoms, and molecules, they have zero dipole moment because Hamiltonian always commutes with parity. So Hamiltonian, let's see, we don't have a name for the parity operation. I'm just going to say parity. So Hamiltonian always commutes with parity, and what that means is for isolated electrons, atoms, and molecules have zero dipole moment. Now we of course saw the case of water molecules, right? Water molecule is inherently polar, and so for that, P is not equal to zero. And so where does that contribution come from? So we need to take a look at the case of a water molecule carefully. And what happens there, the total dipole moment is going to be the nuclear dipole moment, right? Because nuclei themselves are a charged uh, entity, and so they can have a dipole moment. And then you have an electronic dipole moment, and the electronic dipole moment you can see is going to be d cube r rho of r cubed, which you can write down as the expectation value of the r operator for whatever the electronic wave function is, right? And so psi e are the eigenstates of the parity operator applied to electron coordinates alone, right? Because we have specifically looking at only electron degrees of freedom. And so the total one, so you would have corresponding psi n for the nuclear. And in general, then the wave function is going to be the nuclear wave function plus the electronic wave function will be also invariant under parity operation. So for that, what we have seen so far, this statement is still holds true. The total dipole moment is zero, but PE may not be equal to zero. Okay. So individually, PE may not be zero for some molecules, but for the total dipole moment P, which includes the contribution from both the nuclear and electronic contributions, that is going to be zero. Everybody with me so far? Again, you will have to think about it, read through the textbook for the detailed discussion. I just wanted to give you an idea that there is nothing odd with this statement that we got from a general parity expression, right? General expression for the isolated electrons or atoms or molecules. They have, if they have definite parity, then the dipole moment has to be zero, and that's what we are seeing here. Okay, so let's now take a look at another sort of idealization that we normally use in uh, electrostatics, which is the dipoles are used as a point dipole. But before I go there, anybody has any questions so far? Okay, all right. So let's take a look at now a point electric dipole. And you can see why I'm calling this idealization. If you have a positive charge and the equal amount of negative charge and you bring them together at the same location, right? Their overall charge, total charge is zero, right? So you may say, okay, if the total charge is zero, you're not going to get any contribution. But that's not how it works. The in the multipole expansion, just the first term vanishes, and the rest of the terms we still have to kind of take a look at it. So it's, you have to look at that point electric dipole as sort of a limiting situation. So let's draw a little diagrammatic setup of what's going on, and then we will go from there. So let's first set our origin to be here, right? And then we have two charges at points P. And okay, though, let's see, that's not so. So we want to find the scalar potential at point P. So that's our observation point. And here is our charge, right? So here's our dipole rather. So I'm going to draw the dipole as two tiny circles as charges, and let's fill them up. So we know that these are, okay. And so let's first get the dipole sort of lined up. You have charge plus Q over S, charge minus Q over S, right? So, you have this extra S, you will see why we need that. That's our limiting. And the vector that joins these two charges is minus B. Okay, so, or SP, right? So that's also proportional to S, but not inversely. And the dipole direction always is from negative charge to positive charge. So that's our dipole. And we are going to take a limiting situation where this uh, S actually is quite helpful. All you have to do is put S equal to zero. When you put S equal to zero, the distance between the two charges becomes zero. So you can get then the uh, uh, situation that we're looking for, which is the point electric dipole. Okay, so let's now join all the coordinates. First one, what we will need is the coordinate of the first point. Let's call it R0. Then the observation point is going to be R minus R0 here. And the coordinate of the point itself is R, right? So R0 and R minus R0. And then this one here, so what you really need is the distance of both of the charges from the point P, right? So this vector R minus R0 is crucial. You need to know the position of the negative charge, and you also need to know the position of the positive charge. So I think I should maybe delete this and draw the arrow correctly. Okay, that arrow is crucial from the positive charge to the observation point, negative charge to the observation point. And this one we can write down because now we know R minus R0 and S minus SB. So this is going to be R minus R0 minus SB, right? Everybody with me? That is something that you can do from your vector calculus understanding of what's going on. Now the limit is going to zero. That is going to be what we are going to call a point dipole, right? But as we go through this, we want the dipole moment to be the same Q times B. Okay, so dipole moment does not change. As we bring the dipoles, as we bring the charges closer together. And that's why we have this scaling of the charges themselves. As the distance decreases, the amount of charge increases. And so that's what allows us to do this sort of the idealization. Okay, so let's now see how we would calculate this, right? In principle, you could just differentiate, but we need to be very careful. So we do limit as going to zero, right? That's our first thing. And what we need to do is find the potential of these two charges. So 4 pi epsilon 0, of course, the constant. The positive charge is q over s. It is at a distance r minus r0 minus sb from the positive charge. Uh, so we are looking at the distance of the observation point from the positive charge. And then the negative charge is going to contribute negative q over s r minus r0. Okay, everybody with me so far? Okay, and then let's take a look at this. So remember, limit, actually, why don't I write it here? So recall that limit h going to 0 of f of x plus h minus f of x over h is what? Anybody remembers what that is?
First derivative.
It is the f prime of x, right? And so with this, you can kind of see you have this same structure here, except that the function that is changing is in the denominator. And as s goes to 0, this sb term goes to 0, right? And so we can see the parallels between them. And then we can write down phi of r as negative 1 over 4 pi epsilon 0, because we have x plus h, we kind of have x minus h, that's why the negative sign. Then you have the uh, dipole moment p, which is q times b, right? So because you're just h is actually scaled by b, so you need to multiply by b on both the sides and then adjust that. So that's where the p comes from. And then you have the gradient, which is now three-dimensional derivative of the three quantities, because of the functions being functions of r, not just one coordinate x. You have gradient as opposed to a single derivative. Okay, so what you basically need is a gradient of 1 over r minus r0. And that is dotted with p in this. Okay, and so that's the dipole potential. That's the point dipole potential. And you can see that this is exact. This is not a multipole expansion. For a point dipole, because the two charges are opposite to each other, there is no total Q, and it does not have any of the other higher moments. That's what I mean by exact, meaning no other moments exist. You just have this, right? It's basically comes from Coulomb law directly. Nothing new that needs to be done there. Okay, any questions anybody has at this time about this? Okay, so that's that. We just did this. So let's now compare this with the dipole potential or the dipole moment, dipole potential due to an ordinary dipole is there any difference, right? Ordinary dipole is, has a finite distance between the two charges. This one here is a point dipole, meaning two charges that are very, very close together. And so just remembering how it looks like, it's P dotted with R over R cubed for R much greater than R. Do you see any connection? See, 1/4 pi epsilon is a P dotted with something. It's all there, right? And what's the gradient of 1/R? It is minus R over R cubed, right? Everybody remembers? So they are essentially the same thing, right? The point dipole, even though it's in the limiting case, we found that it is essentially similar looking. Okay, so let's now dig deeper into this. We want to look at the point dipole and write it down as a charge density. Okay. And the way we think about this is, how do we find, once we know the scalar potential, how do you calculate the, let's say you have a way to measure scalar potential, right? You can measure scalar potential experimentally, not directly. It's not a quantity that you can measure directly, but you can infer it, right? By doing careful experiments of moving a charge from some reference point, which is at zero potential, to the point of interest. And you measure the energy required to do that, divided by the amount of the charge that you are moving, and you get the potential, right? Or if you if you cannot really measure energy directly, the way you measure energy is the amount of work done, right? So the amount of energy needed or the work done to move the charge from the reference point to the point of interest. And once you have figured out how phi of r looks like, then you can calculate its Laplacian, and then that gives you the charge density rho over epsilon zero, right? So the dipole, I'm going to write it as, this is actually a point dipole, so I'm going to do it this way. Point dipole charge density R is going to be negative epsilon zero del square of the point dipole R. That's how you are going to calculate that. And so let's do a del square of the expression that we found for the point dipole, which is here, right? So we're going to take this expression, take, of course, the epsilon zero gone, so you, and then the minus sign, so you only have 1/4 pi left. Then you have P dotted with gradient of 1/r minus r0. But now we have this del squared. So what I'm doing again is something that mathematicians would not like, but we get by putting, interchanging the del and del square. So del square, I'm going to just push through and then calculate del square of r minus r0. Everybody with me so far? Okay, so no magic yet. In fact, there should be no magic anytime. I may skip a few steps, but there's no magic, right? So that's what is going on. Now, this quantity is something you are all familiar with, right? Anybody remembers what that looks like? This is coming from chapter 1, right? So don't forget some of these basic sort of expressions, because these are geometric. They have nothing to do with either electricity or magnetism. They apply even in the gravitational sense. These are geometric expressions. Del square of r minus r0, right? So it is going to be negative 4 pi delta of r minus r0. And we actually proved this in the class. So you know why it has that form and why it is 4 pi, right? So the dipole charge, the point dipole charge density is going to be now negative p dotted with delta, dotted with gradient of 4 pi. You can just take it out, so that cancels. The negative sign stays as it is, and then you are left with gradient of delta of r minus r0. Okay, and this is singular. Delta already is a singular function. It varies so rapidly. Gradient of that is going to be, it's going to blow up very quickly, right? So it's not something that seems to be finite, right? It seems singular, which makes sense, right? Because you have these two charges that are very close together, and then you have sudden positive and then sudden negative charge. So it's sort of like having a downward spike for the negative charge and then an upward spike for the positive charge. And these things, if they come, really, really close together, you're going to have essentially a rapid variation in a very, very small change of small length scale, and that's why it is singular. So it's not surprising. That's the negative part. That's the positive part. As it approaches, as the distance between these two peaks approaches zero, you are going to get a singular quantity. So nothing surprising, but it's interesting that you can actually mathematically write down and show that, right? So a remark here is essential. These do not exist in real life, but these idealizations are useful. Right, because things are finite. Even if you take an atom, it is still finite. But still, rho point dipole is useful idealization when we are far away from the charge distribution. When you're really far away, then the distance between those two charges does not matter, right? And so you can think of a real dipole as a point dipole, and you can then use these expressions to determine the, what I'm saying is this relation is useful, not so much the charge density of the point dipole, right? We don't really care about the point dipole charge density. What we care more about is this. So this expression is still useful when you are far away from the charge.
Got it.
Okay, everybody with me? Any questions?
No.
All right. So now let's see if we can write down the electric field, right? That would be the next step. Electric field is something you can almost sort of directly measure as a measure of the force divided by the test charge that you're using. And so it makes sense to calculate the electric field of the point dipole. So where can we use this? I said this expression is useful. Where can we use it, right? So you have the, let's say, a collection of water molecules, and you want to find the corresponding dipole moment from that water. You could use this expression, for example, to calculate that, and you just sum over all of the dipoles that you have. Again, those dipoles are randomly oriented in a liquid, right? So it's not going to eventually, all of those contributions will vanish, right? So overall dipole moment, would seem like it's zero. But if there are external fields that can orient the dipoles in a certain direction, that then becomes useful. That means we also have to investigate what happens when you have a dipole and you keep it in some other external fields, because that's going to affect its behavior. And so we're going to take a look at some of these situations. So let's say, for example, R is not equal to R0. That means, you're not trying to find the potential at the position of the dipole, right? It has to be at a different location. Then you can calculate the electric field, which is going to be, we are using just directly the dipole electric field expression for now, and then we will relate it with the point dipole uh, scalar potential that we calculated earlier. Okay, so that's that. For R is much rather than R. So this is the ordinary dipole. Ordinary meaning charges separated by certain distance, right? Now, if what happens here, if R is equal to R0, in that case, then the dipole moment is going to be -3 epsilon 0 integral d cube R E of R. Let me see, I think that I need to maybe fill in some details here. Give me just a second. Okay, so this is coming from example 4.1 on page 94. And what it says is, you have a charge density rho of R confined to a spherical volume V of radius R, right? And then we want to find out, right? So that's the situation. And the problem essentially asks you to prove that the dipole moment of such a charge distribution is given by -3 epsilon 0 d cube R E of R. Okay, and it is done using Coulomb's law, because you could take this expression, substitute Coulomb's law, do the integrals, and as you do the integrals, you will see that it eventually then turns out to be the dipole moment. Okay, so that math, I'm not going to go through that math. Please, that's your reading exercise, if you will. Okay, so this is just, I'm going to put this in the box because it's something external that's coming in here. And for you, this is going to be reading exercise. Example 4.1. Okay, now make sure you're taking these reading exercises seriously when you're sitting through and trying to make sense of the notes. At the same time, if I ask you to read something, make sure you read through that material, because when it comes exam time, you don't want to try to understand and figure out the details at that time. You need to be able to quickly make out what's happening. And if you have read it before, you will be able to do that, right? So that's how we're going to use this expression for determining the dipole moment of the electric field, right? So we're just moving these things around. So that expression, I'm just moving it around integral over that volume of the total electric field is negative P over epsilon 0, 3 epsilon 0 rather, as R goes to R0. So we're now approaching that point, and that's how that that is going to be for a point dipole. Right, so the volume does, you don't really care about where that dipole is coming from, whether it's an ordinary dipole or a point dipole. This expression would be valid in both cases, and we are just taking this R equal to R0, meaning we are very close to the charge locations when we are trying to find this position, right? So let's remember what is R and R0. Okay, I'm going back to show you the diagram, right? So R and R0. R0 is the location of the first charge, and R is the observation point. If R is equal to R0, that means you are able to go within the volume of charge. And that's what we are doing here. Okay, so let's continue. What I wanted to show you is that's how we're going to okay, so that's just the relation that connects the two. We haven't really figured out how the electric field looks like. And so let's now look at again in polar coordinates. Where the electric field now is going to be a function of r and theta, the two polar coordinates. We're looking at the flat plane because the field, if the dipole is in the z direction, that's how it's going to look like, because it's always p dotted with something, right? So it brings it down to the 2D plane, 2 cosine theta r hat plus sine theta theta hat. We know how this one looks like, right? Now let's take this expression, put it back in here, right? And so that we can integrate over the volume of E r and theta, and that d cube r, and that is going to give us, any thoughts what is that going to give you? You have r theta. Let's, because it has two vector components, you would integrate 2 cosine theta term first and then the sine theta term first. And theta varies from 0 to 2 pi. So what's the integral of cosine theta d theta? Anybody? So I'm asking you this: 0 to 2 pi of cosine theta d theta. Yes, 0, and 0 to 2 pi sine theta d theta is going to be 0. And so that gives us 0. Okay. We are taking to be a spherical. Okay, so if we are very close to that, it looks like the electric field integral over the whole volume of space is 0. Now let's take a look at at all points. And so what that means is, see, so if you look at this, the total integral is Okay, I'm missing a step here to explain to you what's happening. Give me just a second. Yeah, okay. So let's add one more term to see if this looks okay. So what I'm going to do is I'm going to basically ansatz here, add a guess in the expression. The reason why we need to add the guess is because if we take this expression and we integrate that, that is giving us 0, right? But it is supposed to give us the total dipole moment. We know in this case the dipole moment is not 0. That means that expression is probably not completely correct. The reason being, remember, this expression is valid only in the r not equal to r0 region, and this is the one that's valid when r is equal to r0. And so the two regions are sort of being treated separately. If you want to use the superposition principle and make sure you are able to write down the electric field in all region of space, you need to combine these two terms, right? So that's the idea. And then I'm ansatz, because I'm just making some guesses for the coefficients. You can check those coefficients later on. Okay, so this, remember, we separated these two regions. What I'm doing now is combining them, right? So this is now the electric field at all points in space. And then we include, that is, it means including r greater than r0 as well as r tending to r0. That's what I mean by all points in space. Then we can write down the electric field to be the expression that we are familiar with from our multipole expansion dipole theorem, which is this. N hat, I'm just bringing in a slightly, let's see why n hat, let's just use r hat multiplied by r hat dotted with p minus p over r cubed. Remember, this is valid only when you are far, far away from that volume. But what if you are not? What if you're closer to it? And then you get 4 pi by 3 p delta of r minus r0. There, the electric field is governed by the delta function, right? Because you are very close to it. And it's similar to this point dipole charge density, right? If that's the charge density, you know the electric field gradient is going to be uh, uh, proportional to, let's see, from the divergence theorem, you can get this, and then you convert it into the integral theorem, Gauss's law. And that's how you get this 4 pi third and the delta function. Okay, so let's remember r is, we did a little shortcut here in writing the expression. R is actually r minus r0. R hat, a vector cannot be a scalar, right? So we just try to write down the scalar quantity, and r hat is going to be the vector r minus r0 divided by its magnitude, right? So nothing new. And then if you wanted to verify integral of the electric field over the volume of space is going to be the first term we know already from the polar coordinate expression that it's going to be 0. And so all that is left with is the integral over the second term, which is negative 4 pi thirds, the dipole moment times delta of r minus r0 d cube r. And that just gives us 4 pi cancels. You have a negative sign, p over 3 epsilon 0, which is what we needed, right? If you look at it, negative p over 3 epsilon 0. So you're able to get both the terms. The terms, the electric field is like this for r not equal to r0. And if the position of the dipole itself is the observation point, we want to get closer to the charge distribution, then the expression that we got from the multiple expansion is not sufficient. Remember, it only is valid within this range. And so that's why we need to add this. So these are near term, if you will, near terms. And this is called or near field terms. That means you're getting close to the charge distribution. And this is the far field terms. And both of those are crucial, right? Because depending on what you want to do, if you're far away, then it's fine. But if you want to write down a general electric field expression, it needs to include that. And that's the near field term when you're close to it. And we got that from the dipole system here, right? So the point dipole structure, right? So we saw that it looks like this. So then the charge itself looks like that, and then we combine those two to give us, essentially looking at this, combination of Gauss's law and that Laplacian expression that we had for the point dipole electric field. That's how you get that. Everybody with me so far? You're trying to understand, conceptually you understand what's going on. Mathematical details, you have to work through them one or two more times. Just seeing me doing it once is not going to be enough. You need to write down and make sure you are able to make those conceptual jumps as you go from one mathematical statement to the next one. Everybody with me so far? Okay. All right. So now we are close to at 9 o'clock. I don't think I will be able to do the magnetostatics part. Maybe just last 2 or 3 minutes to explain to you or just to review. But let's go to the next step, which is the dipole force, which is an important concept. And then we also will take a look at the moment of force, which is the torque in this case, right? So you have, whenever you put a charge distribution in an external electric field, so that's why the coordinates are different. E rho of r prime and E of E of r prime, of course, right? It has to be at the location of where the rho of r prime is. Then we get the force, which is essentially Q times E, but because now you have spatially distributed charge distribution, you have to integrate over that r prime variable, rho of r prime multiplied by E of r prime. Right? So very simple. We need to see what happens if the electric field is external, but we are now the charge is replaced by a dipole force, let's say. So we're going to now assume that electric field E of r is slowly varying. That means we can do a Taylor expansion of it. So E of r prime at some point is going to be at some reference point E of r plus the standard three-dimensional Taylor expansion that we saw in the first chapter. E of r, the first derivative term is converted into a gradient dotted with r minus r prime, and so on, right? So we're just only going to look at the first two terms, and r prime essentially here is r plus h, where h is a small quantity, r minus r prime. So if you want, this here is essentially h, and so on. So it's the small change in the distance from the points h started with, and h itself is a vector, right? Because it's r minus r prime. Okay, so that is just to recollect that's how these things are connected. Now the total charge causing this is a given information. The electric field that the external field is, it's coming from, let's say, a total charge that's zero. That means maybe it's just the dipole field, right? So F is equal to, then in that case, d cube r prime, rho of r prime dotted with the gradient applied to E of r at r equal to 0. So it's only this term that's important so far. Let's see what's happening. If r is slowly varying, so that's just the second term at r equal to 0. Let's say E of r is, this is actually just the second term, actually not the first term, right? Because you have this r dotted with delta, r dotted with the gradient rather in there, applied to the electric field, which is the second order term, and then you multiply that by rho of r. So the first term essentially is 0. Okay, so that's that. Let's now connect it with the definition of the dipole. So the dipole is defined as the volume integral of the charge distribution multiplied by the position coordinate itself, right? And so if you look at F, then it looks like, because of this r prime delta, remember the gradient here is with respect to the r coordinate, and the integral is with respect to r prime coordinate. So you can interchange the order. And so when you interchange the order, what you are going to get essentially is integral d cube r prime, rho of r prime multiplied by r prime. So that's p dotted with gradient applied to the electric field, right? So that's how that looks like. And this part is all that is r dependent. Sorry, this is also r prime dependent. So I'm going to write that as p. And so you get the dipole force to be this. So if your charge distribution is, okay, so if your charge distribution is a dipole and you put that dipole in some external field, this is the force on the dipole. Okay, so let's write down what this is: force on a dipole in an external electric field. Everybody with me so far? You understand what we have done? So we started with first the standard Lorentz expression for the force, right? And then we replaced it with we replace the electric field as some slowly varying electric field. Because why do we have to do that? Because dipole is not normally a point, right? It has certain size, but very small. And so to be able to arrive at that, we're doing this, right? And then the total volume charge is 0. So it's only the dipole that matters, the dipole moment. And so that's what allows us to calculate this. Okay, everybody with me so far? So that's the force on a dipole. Let's now see what happens in if we have a uniform dipole field, a uniform electric field. So I'm going to just draw some electric field lines here, uniformly distributed. What can you guess? If it's a uniform field, what do you think will P dot delta be? P dot del be? Anybody has any thoughts? I'm going to draw the dipole here. Remember, dipole now is a vector that has some special extent, right? Because of the charge separation. And that's our dipole there, E. This charge is positive Q, that charge is negative Q, right? And the dipole direction is always from negative Q to positive Q. What you know from the standard um, uh, properties of the uh, force on a charge kept in an electric field, what should be the direction of the force on the positive charge? Actually, maybe I should. I'm going to change the arrows here. Let's say the electric field is that way. So what would happen to the positive charge? Which way would it move? To the left or to
Like
the right?
opposite of the arrow for the positive charge.
Opposite of the arrow for the positive charge. Why? F is Q times E. Q is positive, so it should be in the same
Yep.
direction as the charge, right?
Yeah, same direction.
Or,
So for the
or
negative
am I
charge,
making any mistake?
no, for the negative charge, it's in the opposite directions.
Okay, very good. So that means the force, okay, I think I should use a different color for the force. I'm going to use this color for the force. So F positive is that way, F negative is that way. And so what's the total force on the dipole?
0.
0, right? Because the dipole is not going to move in the direction of the electric field if the electric field is uniform. But what else is it doing? Because you have two equal and opposite forces tugging along on the ends of the dipole. What's that going to cause the dipole to do?
Spin.
Spin. Very good. So you have a torque. So you have a non-zero torque in a uniform. Uniform is important. In electric field, but there is no force, right, on a dipole in a uniform. Again, uniform is important. So you're going to have the dipole is going to try to orient itself in along the direction of the electric field, right? So we should be able to evaluate the torque, right? And so that's what we're going to do. So this gradient here is extremely crucial. If the electric field is uniform, it does not vary, then there is not going to be any force on the dipole. If the electric field varies, then which way the force is going to be. Okay, depends on the orientation, relative orientation of P as well as the gradient. And so if let's say you have a gradient moving in a certain direction, let's say gradient of the electric field is towards the right, then what's going to happen to the dipole? Which way is the dipole going to move? Any thoughts anybody has? It's actually gradient in some random direction in a direction perpendicular to P does not matter, right? Remember what we are looking at here is P dotted with the gradient. That means only if the electric field is changing in the direction of the dipole moment, which is Z. So if there is a vertical in this diagram that I have here, right, in this particular one, only if E has a vertical gradient, Yeah, that means along P, F will be non-zero. Everybody agrees with that statement? P dotted with gradient, that's what that means, right? If the gradient is in the direction that's perpendicular to P in the horizontal direction, then no force. Then, oh, no, sorry, I said this wrong. You guys did not catch me. Only if E has a vertical gradient that's along P, F, yeah, no, I think I said it correctly. F is non-zero. And if E has a gradient only in the horizontal direction, then P dot gradient is still zero. And so F will be zero. So there are more situations when the force on the dipole would be zero, right? And then the torque, of course, would change also. This situation is idealistic, simple. I can draw a diagram for it. The other ones are a little tricky, so we need to look at them kind of more in details mathematically. Okay, so let's now dig deeper. We have maybe 3 minutes, so I don't think I will be able to do this, but let's try that out. So we do a gradient of the quantity P dotted with E, which is going to be P crossed with curl of E plus E crossed with curl of P. You know this from the back-cab rule. And so because we have these two combinations, one of those terms will look like the ones that you're looking for, plus E dotted with gradient times P. Okay, so this vector identity you could prove for yourself. I'm not going to go there, but we know that curl of E is zero. P is a constant vector. So some of the terms will go to zero. For example, because of this, E dotted with gradient applied to P is going to be zero, right? Because P is a constant vector, that doesn't work. So the first term is zero, the last term is zero. You only have two other terms remaining. And so what you get is P dotted with gradient of E is equal to divergence of P dotted with E. Let's see what happens to del cross P. Oh, even the second term is zero. So I'm going to highlight the terms that are zero. This is zero, that's zero, because P is a constant vector. And the first term is zero because of this. And so only one term remains. That means P dot gradient of E in the above expression that we found can be replaced by gradient of the total quantity P dot E. And that just kind of makes things a little bit easier to understand and evaluate, right? So I reformulated this term here, P dot E. And so then this implies that the force is going to look like gradient of P dotted with E. That's much easier to evaluate actually. And so this is going to be the instantaneous force on the dipole. Okay, so let's take a look at now a point dipole, force on a point dipole, where there won't be any torque because the two charges are very close together. So point dipole density, we know rho of D of R. So then you can calculate the force, which is the volume integral rho D of R let's do it the volume integral over the coordinate R prime, E of R prime, and which is then is going to be P dotted with integral of D cube R prime, delta of R minus R prime. We know how the expression for rho D that we saw earlier. times the gradient applied to E. Okay, so what that delta function basically means is that the point dipole has a fixed position. Right, so what we are basically doing is, we're replacing the we're replacing the position of, replacing basically rho d with the delta function because it's now fixed in space. And so at that position in space, you have to calculate the gradient of the electric field, and that's going to determine how the charge is going to move. So for a charge, the force is given by the electric field itself. It's proportional to the electric field at a point in space. But for a dipole, the force is proportional to not the electric field, it's proportional to the gradient of the electric field. If there is no gradient, there's not going to be any force. And I think I don't have time to go through the torque discussion, but we will do that in the next class. And it's these things may look complicated mathematically, but they are more complicated to analyze and understand what it really means. So make sure, even when you see a simple expression like this, box expression f equal to p dot gradient of E, you want to be able to understand its full meaning and what it means, what is happening geometrically speaking, because you have you have these gradient like quantities there.